Okay, so our next little project here is something I just picked up. And it's a Sencore SG-165 stereo analyzer, AM/FM stereo analyzer. And this is a unit that I already have one of them, but the one I got was in pretty bad shape when I got it. I was able to bring it back and get it working perfectly, but the power supply in it was so bad that I actually had to remove the whole power supply board and make up a new power supply board with updated components that put out the same voltages to get the thing to work. But once I did that, I was able to get it to dial in perfectly. But this is a must-have for anybody who does a lot of work with AM/FM receivers, especially the newer solid state ones versus the old tube ones. But even with the tube ones, there's lots of test equipment out there that can do what this thing can do. But this is a really unique machine in that not only is it a signal generator, but it is also part of the measurement equipment that you use. So if you notice, you have a couple of power meters here, and they read the power output of the amplifier, but they also serve as like meters that read, and you can see these things have from the static electricity of my fingers, you can see how they react. But anyhow, these actually read the output in watts and can allow you to like set the peaks on IF stages and things like that. But it also has an RF signal generator. It has IF signals, multiplex for doing stereo. It does square wave and sine wave testing, crystal controlled oscillator. It does AM and FM modulation, right and left channels. It'll put out a stereo pilot. It has a watt meter to check the wattage at different speaker impedances, and it even has markers for doing FM alignment. Now this particular unit, I just got it, and it seems to have a lot more issues on the inside than it does on the outside. So I don't really want to turn this on and demonstrate it anymore for anybody because I think there's some issues with it. But I got the 10.7 megahertz. Anything that's the RF part doesn't work at all. The markers I think work. These don't work right. They're real rough moving, and I think somebody tried to work on it. So anyhow, let's get this thing apart, and we'll go over a little bit more of what all it can do. The first big issue I see right away is right here. This is all melted and trashed inside of here, and that's obviously from this resistor bank, which this is the dummy load resistor. Each of these is 16 ohms at 22 watts, and there is 1, 2, 3, 4, 5. There's 10 of them all together, and it looks like they just got way too hot. And it looks like somebody tried to replace them or something maybe, and it just melted this whole meter assembly. Now I don't know if the meter still works or not. It looks like it may, but definitely not good. So there's our first problem. Other than that, I see some wiring back here that may not be original, but it may be. I'm not sure. A problem that every one of these things has is if you look down in here, right there, this is the tuning knob for the RF, and as you can see, it's just a plastic shaft. Every single one of these snaps and needs to be replaced with another shaft. So I'll have to make another shaft for this, or make a new coupler or something, so it won't tune. And these are all just things you can expect to find. You know, the melted thing, no, but that broken shaft. And this power supply here is the power supply I was talking about. On mine, this whole board's gone, and I made a new board with modern voltage regulators to get the power that I need, and to also to pick off this is what one of these adjusters is actually, if I recall correctly, is your adjustment for your sweep, your 60 cycle sweep. So anyhow, I'm going to dig into this a little further and see where we're at. I'm going to test this meter and see if it still works even though it's melted, and then we'll go from there. Well, after some pretty extensive service, this thing is perfect and it's back to life. I did find some issues. One of the things that we did was I updated the old RCA jacks, as you can see. I updated those to BNCs to make them easier to connect to our modern test equipment. And I added these jacks. Originally, this thing had just a set of leads coming out the back to connect your amplifier to it. I think these banana plugs will be a lot easier to deal with. The good news is this melted meter did not, it still works. I mean, the plastic is melted, but the meter movement is still good and intact. Now, here's some of the things we had to do, turning this around. These resistors were really botched up bad. The wires were melted. Somebody put way too much power in this watt meter, and it really damaged it. I had to clean all these terminals. I had to put new wires in there that weren't melted. But it came out and all the resistors still tested good. They still worked. So we were good there. You can see where I wired these in. I replaced the capacitors, just the electrolytics, and tested the power supply. It was almost dead on. As a matter of fact, this whole machine was pretty well calibrated when I tested it. It was off a little bit, the dial scale and some things. A major problem with these is the tuning dial for the RF generator uses this little plastic nylon shaft. It's like a shaft extender. It's drilled out in the end, and there's a little knurled piece here at the end. You can't really see it, but a little knurled piece at the end that this slips over and then attaches to the collar, the little set screw collar for this little tuning knob. So we had to fabricate one, and as it turns out, this little piece of aluminum tubing that I got at the hardware store fit right over that knurled shaft end perfectly. So what I did, as you can tell, losing my voice, it's a different diameter. So what I did was, after I slipped that over the end, cut it to the proper length, I just took several pieces of heavy marine grade heat shrink tubing and built this up until it was the right diameter. Then it just slipped perfectly, as you can see. I don't know if I can zoom you in or not. See where we're at. There it is. Zoomed right in, right there. Fit right into the shaft, and I tightened the set screw, and we were good to go. So again, if you buy one of these things online, there is a high probability that that little piece of plastic will be broken. It's just a known issue with these. Inside the oscillator chassis, which is what's inside here, right here, inside the oscillator chassis, there was one large capacitor right here, and although the cap checked good for capacity, it was off a little bit. It did check pretty bad for ESR, so I replaced that. The other issue was, they call this an L pad, and it is connected to the output of the RF, and it's this knob down here it's your output control. This L pad was bad. The shaft was very wobbly, and it's broken inside. It also looks as if somebody had tried to work on it and miswired it. So I found a new old stock pot. The problem is, this is a 75 ohm potentiometer, if you look, and you can't find those anymore. They're really hard to find. But I had in stock a new old stock long shaft 100 ohm pot to go in here, and you can see it came with like a brass, right there, brass shaft on it, and I was able to put that in, and I shunted a resistor across it, and I think it was like a 2 point something K. Basically all it did was it took the 100, but by going across the two outer terminals of the pot, I changed the overall value of the pot to about 75 ohms. And the way this thing's wired, I can get away with that. So that's what I did. It works perfectly. I cleaned all the controls and deoxed it and all that stuff. And then I went through the alignment. Now, when you do an alignment on these, this is test equipment, so your accuracy is very, very important. So for instance, there's 4 calibrations for this to make sure that the dial is accurate on AM and FM all the way across the dial. And that takes some real time to get that all to balance so that it is. This one's tracking absolutely perfectly now. The other thing is each one of these, the 10.7 megahertz IF, 455 kilohertz, 262 kilohertz, all of those need to be calibrated. And I did those. There are multiple ways to do it, and maybe we'll do a little demo on how we align this RF circuitry like this. There's 3 different ways that that you can do it, probably more than that, but I'll show them to you and you'll get an idea. Now this is all lined up, so I'm not going to touch the alignments anymore because it's fidgety, but I'll show you how to hook this up if you were going to do it, how to do it. And then we'll go a little bit into what this does and how it works. Okay, so right now I kind of have this set up with my scope that I take out in the field with me. It was really cold out there, and I kind of brought it in to thaw out and let the battery charge up on it. This is a really good oscilloscope. Let me show you this for a second before we get into anything else. Let me move this over and let you take a look at it. This is a definitely a foreign-made scope, that's for sure. And it is made by a company called OWON, O-W-O-N. And this one is a model SDS7102V as in Victor. And it's a 100 megahertz scope, 1 gigasample. It's a very modern scope, and this thing can be had for about $350, $300, which I think is a fantastic deal for what it is. It has a great big screen. You can see the size of my hand here, how big that screen is. And it's pretty full-featured. It does a lot of things. And really, for the money, you can't go wrong. And I'm going to show you a little bit of what we can do with a modern, low-cost oscilloscope when it comes to measuring the output of our test equipment. So, really, I told you there were 3 different ways that we can measure to calibrate these signal generators, okay? And the first way we're going to look at is the oscilloscope method, and this is probably the way that most of you will do this. If you do have a need to calibrate a signal generator, you get something online and you want to restore it, here's one way that you can do it. So if you look right now, the way I have this set up, I have the signal generator set to 10.7 megahertz crystal control, continuous wave only. What that means is it's just going to put out a carrier, just a pure 10.7 megahertz sine wave, which is what you would use to align, for instance, the IF section of an FM receiver. Okay, so this is a really good setting right here, really good function that this machine can do. It also has a 10.7 megahertz that's adjustable, coil, just a typical oscillator, not a crystal controlled oscillator, and you can actually add modulation to that. So if you need to do a modulated FM IF, you'd go up to here. But if you need a really accurate 10.7 megahertz signal, this is where you could go. So we're looking at that signal, coming out of the output of the machine. And if you notice, there it is showing up on the scope. Now, even if you don't know much about oscilloscopes and you're just getting into this, when you have a consistent signal like this, meaning it's a pure, nice sine wave, it's continuous, it's not varying or changing, most modern scopes have a little button called auto set. So if you look up here, there's a little button that says auto set. Now, auto set's kind of a, for those of us who are really into electronics, that's kind of like cheating. But what it does is you get your signal on your input of your scope, you hit auto set, and it automatically sets all the dials to where it thinks they should be to get your waveform to display properly on the scope. And that's what you do there. Okay? Or you could manually go through and set everything, but there you go. Now, another function that a lot of scopes have, even this little $350 job, I think $350 for this. Oh, hold on. Okay, I'm back. So anyways, so one of the things we can do, even with this low-cost scope, I mean, you're talking, you know, $300 and some scope, there's a button up here called measure. Okay, so if you see measure up here, I'll zoom you in, measure. Okay, and basically this measure button allows us to do something here. If we hit the button, we do measure, and I go add. Okay, add measurement, and I want to measure the frequency, right? So if I do frequency, there you go. So I have the frequency, and I do add. And it should add that in there. Oh yeah, I'm sorry, I already did it. So it shows up down here at the bottom of the screen, and you can see .7 megahertz. Pretty cool, huh? So your oscilloscope can actually act like a frequency counter. Okay, so not only will it show you the waveform, but it will measure the frequency. Okay, so that's very useful. So let's say we were in this setting here. This is not adjustable because it's a crystal controlled thing. There's no calibration. However, in the service manual, there is a calibration for this one. Okay, so, and it's not quite as accurate as the crystal, but it's pretty good. And so there would be a little adjustment slug, a little coil you're going to tune to set that frequency right at 10.7. So what you would do is you'd go over here and you'd look at your waveform, and then you'd go down to here and you would adjust until it gets right on about 10.7 megahertz. We're right about there now. See, it's toggling around right at almost 10.7. Okay? Very easy. Now, same thing for the RF tuning. So if you go to RF, okay, and we move over to here, you notice what happened to our waveform. It's different, right? Because it's a lower output. So what you want to do is hit your auto set button again. See if this thing picks up on it. Yeah, it actually did. And you can see the RF oscillator in this thing is not perfect. I mean, it works, but it is not a perfect sine wave, and none of these really ever are. Sometimes they do this for a reason. They want to have some harmonics to be able to pick up on higher frequencies too, pick up the harmonic. But we'll get into, don't really want to get into that for this one. So anyhow, if we look here, I'm set at about 98, 99 megahertz. Let's just get this right in there. I have my dial set at 100 megahertz. See there? Right there, 100. And if you look, can you see that? 100 megahertz. Okay, so, and you can see as we adjust this, the waveform gets bigger and smaller. Okay, and the frequency changes. You can see it changing. And remember, why is this thing shrinking? Well, I don't have a good impedance match. I'm using a test lead that's coiled up wire. I don't have this terminated. There's a lot of reasons why the amplitude and shape of the waveform will change on this, but when you're using it in the real world, it does, it works. That's how these things function. But anyhow, so that's the one way that we can check frequency. Okay, so I'm going to go back to my 10.7 because that's a nice waveform. There we go. And that's method number one for measuring the frequency while you're adjusting a signal generator. And again, it's not just this Sencore SG-165. It could be if you're setting up one of these, this is a real old vacuum tube signal generator. It could be, any signal generator that you're trying to calibrate frequency, or even a tuner for that matter. You're looking for, for frequency. That's a way to do it. Now, let's go to method number two. Let me get set up. Okay, method number two, we're going handheld here because this is way up on my bench. I don't use it very often, so it's at the top where I don't use it. But if you notice, we're using a frequency counter, and this is a very low-cost Chinese. A lot of, any real electrical engineers are cringing right now, but it really does work. And you can see, you just plug it in to the counter into the correct range, and you set this thing up, and it directly reads how many megahertz? 10.6978, so it's 10.7 megahertz. And you can see down here, we're set to 10.7 megahertz. And all you do is you would make your adjustments, and same thing, you would be able to make your adjustments and use that. Now, that's a pretty accurate way of doing it, and it works. You cannot see the waveform, but it will work. Okay, and again, it's accurate. Okay, so that's method number two. It's very simple, and you can buy those frequency counters relatively cheap. Those ones up there are in the $100 range or so, brand new. Of course, they're made of fine china, and they're not the highest quality. But as you can see, we have two pieces of low-cost test equipment that are very accurate and working very well. So you don't have to be wealthy and have, really high-end expensive equipment to do some of the things you need to do on your bench if you're just, trying to do bench, doing repairs on a budget. Okay? So method number one is the oscilloscope and use the measurement. And even these older scopes, like this Tektronix here, they do have a rudimentary measurement function. They don't always work quite as good, the old scopes, for measurement, although they do. They work. But these new ones are really slick. They just directly read out frequency, and really nice. Now, the last one is going to be a little bit out of most people's budget and out of most people's range, and that is over here. We're going to show you what it looks like on the spectrum analyzer when we're aligning, and this is what I use to align this. I use the spectrum analyzer, and I'll show you why here in a minute. Okay, so last of all, we have our spectrum analyzer, and even an old used one that is in good working order, that's calibrated properly, is going to be very expensive. You're going to spend, over $1,000 for a good one. And very easily, some spectrum analyzers today can be in the $10,000 to $20,000 range if you buy a really, really, really good one. But even ones with the lower bandwidth, you expect to spend $1,500 to $2,500 for a good one. You can take your chances on eBay and buy, you know, a whereas as is, but this is a precision piece of test equipment, and if it doesn't work right, you just waste, even if you buy it cheap, you wasted your money. Now, a little bit about spectrum analyzers. They are similar to an oscilloscope in some ways, but they're different in others, okay? So for instance, this one, when you look at the horizontal, okay, this thing is measuring in the frequency spectrum, okay, whereas an oscilloscope is measuring in the voltage spectrum, okay? So they measure in they both measure in different manners, okay? So frequency is going to show up right to left, kind of, sort of, and amplitude of that frequency will show up in the vertical, okay? Whereas the oscilloscope is actually showing a sweep, a time sweep, okay? And it's showing a voltage versus time, okay? It's different how they lay it out. So first thing you have to do when you're using a spectrum analyzer is you have to set the parameters to what you're going to measure. Right now, when it comes up, and if you notice here it says oven cold, you don't want to really take a measurement if you were going to calibrate something when that message is being shown. What that means is this scope here has what's called an oven. And what the oven is this has a crystal oscillator, but it is temperature controlled. See, quartz crystals can actually shift their frequency a little bit with temperature. So the only way to ensure total accuracy is to have a regulated temperature on the crystal. So what this does is it has an oven, which is nothing but a little heating element inside of a box, and this crystal is in the box. It heats that up to an ambient temperature and holds it very accurately at that temperature, which stabilizes that crystal oscillator. And that oscillator is the reference for this scope. That's what makes it so accurate, okay? And then on the back of the scope, if you need even further accuracy, there's a port for a reference signal, a 10 megahertz reference signal, and you can actually get like an atomic rubidium frequency standard, they call it a frequency standard, and make this even more accurate. But this machine's calibrated. I just want to show for the purpose of what it looks like. So oven cold, we're not going to worry about that. But normally you would wait for it to warm up and stabilize. You would wait for everything to warm up, even your test equipment that you're calibrating. I would never start an adjustment until this thing's been up and running for about a half an hour. And that's just to make everything stabilize. It will drift. It's analog equipment. And it will drift as the temperature changes. So it won't stabilize its temperature until it's been on for a while. Half an hour is a good rule of thumb. So the first thing we do when we use our spectrum analyzer is we have to figure out what frequency we're trying to adjust it to, okay? So for this instance, it's 10.7 megahertz. So if you notice there's a frequency button, that's called your center frequency. That's the frequency that the center graticule is going to represent on the horizontal. So if I push frequency 10.7 megahertz, and there's my center frequency. It's showing where the center frequency is going to be. Then when I hit span, the span is actually what range of frequencies I want to display on this screen from here to here, okay? And I'm only going to put a span of about maybe, let's say, 10 megahertz, okay? Span 10 megahertz. That's a pretty wide span. And if you notice, that disappeared, okay? I have everything set properly now. Now let's plug this in, and what happened? You see it? You see a peak there. So that's actually showing you what frequency or frequencies are being displayed. If you notice, we have a very nice crisp peak, and there's no down in, this is called the noise floor, down at the bottom here, you don't see any other little bumps like this, which would indicate that there's other signals or other frequencies or other interference on there. So this is giving me a lot of information, even though it just looks like, you know, a Christmas tree. But this is what it is. Now, on a spectrum analyzer, you have a button called a marker. And a marker is just a little blip that it'll put on the screen at whatever frequency you want it to monitor. So if I do peak search right there, see the little diamond that showed up? It found the peak, and then up here where it says MKR, it's telling you what frequency that marker is placed at. And since the peak of my signal is lined up with the diamond, then my signal is peaking out at 10.7 megahertz. You see that? See where it says that? 10.7. So once again, it's showing us the frequency. All right? Now, here's where it gets interesting. Let's say I want to go to RF. I just switched it over to my FM RF signal generator. So now it's generating RF. I, of course, want to change my frequency, right? So I'm going to go frequency. And let's say we want to go to 98 megahertz. And you can see where that peak is right now. All right? Now, right there, our marker is sitting at 98 megahertz. Okay? You follow me so far, I hope? And as you can see, our signal is not there, but watch what happens, okay? I'm going to rotate this knob right here, RF tuning. I'm going to just turn this. I'm not going to touch anything else. I'm going to turn that, and I'm going to focus you back on here and watch what happens as we do this. I'm not even going to use the dial scale on this thing. I'm just going to use my spectrum analyzer. See the peak? See the marker climbing up on the peak? Watch this. There it is, right at the top. I am right at 98 megahertz right now, right? Now let's take a look at our dial scale and see where we are. Pretty good, huh? And again, I have the camera's at a little bit of an angle, so this graticule being in front makes it look like it's a little off, but it's really close. Pretty much right on 98. This is how you would adjust your dial accuracy. So you would set the dial right on whatever frequency you want to calibrate to. Then you would set your center frequency to the target of what you're trying to adjust. Then you would go in and you'd take your little tweaker and you would adjust your coils, or you would adjust your trimmer capacitors until you bring this right dead center onto your frequency. And that'll make the dial line up with the oscillator, line up with the spectrum analyzer. And you can see how nice it is when you're calibrating something with that, because you can actually see right where you are. You can peak it perfectly. Now, one of the problems with like a frequency counter is they can false trigger on noise and things, and if you don't have a really perfect waveform, sometimes it'll jump around a little bit and you kind of have to keep watching it. But this actually gives you a very good representation of what's going on frequency-wise. So, now, a couple caveats about a spectrum analyzer. Number one, this is one of the most delicate pieces of equipment that you would have on your bench. The input, the rules are very strict about this. This has an input impedance of 50 ohms. Okay, so if you're measuring the amplitude, you have to understand everything has to be terminated correctly. You have to have the right wire, the right everything. Number two, maximum input, okay, is 0 volts DC. Okay, so let's go down. And I don't know if you could see it underneath this, but let's unscrew this for a minute. 0 volts DC, okay, and 1 watt or plus 30 dBm max. That means if I put any DC whatsoever on there, I will probably damage the little preamp or the little buffer amplifier at the input of this terminal. So if you are plugging test equipment or plugging a signal into that piece of test equipment, you better be really, really sure that you do not break those rules, or you may find yourself with a giant multi-thousand-dollar boat anchor, and that's not good. So I would recommend, there's a gentleman who is just fantastic. He probably in his pinky finger has about 10 times the knowledge I'll ever have, and he has a YouTube channel called Mr. Carlson's Workshop. Okay, I think that's what Mr. Carlson's Lab, and he's out of Canada, and he does a couple of really fantastic videos on spectrum analyzers. And one of the things that he shows is a little isolation pad, and you can see here that he built and designed his own little design, which is genius, to protect that. This basically will isolate the signal that's coming into these leads from the signal coming out and going into your spectrum analyzer. Anytime you're working with tube gear or anything that may potentially have a DC voltage on it or exceed the input level, of the signal, this will actually not only isolate the DC away from the spectrum analyzer, but it will also limit the maximum signal. It actually will clip it off above a certain range. It's a fantastic little device. I'm not going to get into it, how to make one. You can go to his website, Mr. Carlson's Lab. And like I said, I love giving credit to people who are really do so much good for the community by sharing their ideas like that. So catch his site. You'll be highly impressed with all of his work. So anyhow, those are 3 different methods that I've demonstrated how to calibrate a signal generator. Now, I didn't go through the calibration of this for several reasons. Number 1, it's very touchy and time consuming. Number 2, you've seen me adjust radio circuits, like when I did the Hallicrafters and a lot of my radios and tuners. And really the process is the same. You connect your test equipment to a certain output and you measure the frequency and you adjust either a coil or a capacitor until the frequency matches whatever the instructions are telling you to set. And that's really what the process is for this as well. Okay, so there's that. That's part 1 of this video. The second part is just a little bit more on what this thing can do. So let's get our scope back here, and I'll be right back. So we're back to our oscilloscope. What does one of these stupid things do anyways? What do we use them for? So if you notice the way this thing's split up into sections, okay, let's kind of look at this a little more carefully. The top part up here, okay, from here up, is basically a watt meter. This is for connecting an amplifier. You can connect a stereo amplifier. The speaker leads of the stereo go directly into these banana plugs. So this is left channel, this is right channel, and you can see it has a watt meter, and you can adjust it for 4 ohm, 8 ohm, 16 or 32 ohm, depending on what kind of amplifier it is. You can check for stereo separation. You can also check power, and this would be 0 to 10 watt range, and this would be 0 to 100 watt range if we click it over here. All right, now as you saw how melted all that stuff got, somebody overdrove the heck out of this thing and should never do that. Guys, don't use this for a power meter for your, or for a dummy load for your amp. Build a dummy load. Buy two 8 ohm resistors or whatever, and make yourself a nice dummy load and torture those resistors. Don't torture this thing. I'm never going to put more than 5 watts or so into this per channel. And the reason I'm going to do that is if you're aligning a radio, you can connect the speaker terminals to here. Even if it's an AM radio, hook the speaker to one channel, and the output of the meter will actually settle down. This thing's really sensitive to static electricity. The meter will actually read the peak of the signal. So as you get on peak while you're adjusting your trimmer cans, you'll see that meter peak out. It's just kind of like works the same way as using your volt ohm meter on the speaker terminals across the speaker. Same thing. The only difference is you don't have to listen to the sound on the speaker. You use the dummy load in here to take the place of the speaker, and then this meter is actually monitoring it. Okay? So that's the first thing that this thing is. Second thing, it is a full function signal generator. So if you look down here, this thing's kind of split up into 2 sections if you look. There's an AM section for checking AM receivers and an FM section for dealing with FM receivers. Okay? Now let's do the easy part first. This is the AM section. So if you look over here, I'm set to RF. So all that is that's just going to put out the same range of frequencies that your radio tunes to. So if you notice, here's AM kilohertz. And if you look, it goes from 550 or about 525 kilohertz all the way up to 1625, which is the range that your AM broadcast band radio receiver works in. So if you're doing an old All-American 5 radio, or just doing an AM radio alignment, everything you need is on this side. So for instance, if you're adjusting for dial accuracy, I mean, you could dial in your 600 kilohertz, okay, just like that. And as you can see on the scope, you have your 600 kilohertz. And then if you want to be able to listen to the modulation, modulate it at 400 cycles, I flip on this modulation, okay, and it should modulate that signal. Now, I think this might not be working right because you see how it's jumping around. So we will have to fix that. But basically, this will put a 400 hertz tone on the output. Okay. Same thing here. See, my modulation, AM modulation, is not working. I need to fix that because that switch is dirty. I thought I cleaned it, but I didn't get it cleaned good enough. So anyhow, that's RF, and then this will put your carrier wave, and then this would be a tone, a sound that is riding on the carrier wave. Okay, so this would actually be pulsing up and down at 400 cycles. Now, to adjust the IF, you would go to 455 kilohertz. Okay, most super heterodyne AM radios have an intermediate frequency of 455 kilohertz. So this is a preset 455 frequency that you can set your IF with. Older radios and some of the car radios use 262 kilohertz. Car radios use this because, to my understanding, it's more friendly with ignition noise and so forth. This is too close to ignition noise, and you can get a lot of motor whine and stuff like that. This would be a 400 hertz sine wave. So let's say you just needed an audio frequency, okay, and you wanted to just listen to audio, say you're testing your amplifier. You don't want to test the tuner, you want to test the preamp or the amplifier. This will produce 400 cycles. And if you want to check for distortion, you can go put a square wave out, which is 400 hertz also, and that square wave will actually allow you to measure distortion and things like that. So, and then down here, extra crystal, there's actually a socket inside the machine that you could put another crystal, and you could set it for whatever other frequency you want it to oscillate at. So that's the AM. Okay. Now if we go to the FM side, it has very similar controls. Okay. So if we look here, there's our output. Now FM is a lot lower millivolt output than AM. Okay, has a little bit lower, has a lower output. And you can see, and it's like that on purpose. FM receivers, the way they work. Okay. Same thing as the AM, and you can modulate it. Okay. Sorry, okay, I'll be right back. So let me do something for you here, because I kind of want to show you guys what I'm talking about. If I go back over to here, let's I'm going to connect you up to my other SG-165, which is over here, so that you can kind of see what this looks like with modulated RF. Let's see here. Oh, I see here. Hold on. Here we go. Oh, that's interesting. Let's see if it picks up on it. And you could see right there, the scope is actually freezing. This one doesn't do as good of a job of displaying modulated RF. That's really interesting. This is the first time I've ever looked at RF on this little scope. So we're kind of doing a little evaluation of that too. I use this for capturing single waveforms like on X-ray machines. It works fantastic. I'm just kind of checking to see what it does with RF now. So let's see if we do this, what that does for us. There you go. So right there is your RF. So let's go back to this one. Maybe it is working. Maybe it was our test equipment. Okay. Oh yeah, it works perfectly. Okay. So I'm just setting a trigger on this a little bit to make it a little more stable. But there is your modulated carrier, unmodulated carrier. And you can see how that looks. All right, modulated, unmodulated. Okay, so this would be your 600 kilohertz we're set at right here with no sound being carried on it. In other words, this would be like just the radio station tuned in without any kind of signal or information being carried on it. This would be a 400 hertz tone. This would be just a 400 hertz sine wave tone is all that would be. Okay, so that's modulation. So again, go back to this. There we go. And I don't think this is going to pick up modulated FM because this is going to be just too hard. The other thing is on this scope, I may have the coupling. Let's see here, trigger. I may have the coupling set to be able to noise reject, which means it won't pick that stuff up. Anyhow, I'm getting off track. So anyhow, this is for your FM, and you can see as I change the frequency. Okay. Then there, we looked at this already, your 10 megahertz, 10.7. Okay. And that's with and without modulation. Then 10 megahertz crystal controlled. Now this next one is called sweep and markers. What is that? Okay. Well, you could see it makes your scope go crazy. All right. Because what's happening is this thing is sweeping. Okay, I'm sorry. So, work day today. Didn't get any field service calls, but I've been getting a lot of phone calls today, so I'll be getting interrupted once in a while. Anyway, see this thing's going crazy. It's because there's a lot of things going on right now that you're looking at on this scope. And first thing is the center frequency is 10.7 megahertz. However, it is sweeping, okay, through a range of frequencies, okay, plus and minus. And that's what you're seeing right now. Now, this marker thing, what is a marker? First of all, the marker on this machine is not coming out of this port. It is up here. And let's see if we can get this scope. Might be hard to display on this scope. Let's see if it picks it up. Oh yeah, I got it. Perfect. Look at that. Now, it's going to jump around because this is a really hard signal to trigger on. So, don't mind that. But if you look at that blip right there, that blip is actually called a marker. And I can adjust it with this marker height adjustment, you see? Okay. And what that marker is doing, this is called a post marker. There's a pre-marker and a post marker. All that means is where you're adding the marker to the original signal. So if I look at this, this is coming out to my scope. Remember I told you very early on, not only is this a signal generator, but it is also a piece of measurement equipment. In other words, you have a special probe that plugs into here, okay, and it goes in. You don't hook your scope into the receiver, you hook this port into your receiver that you're testing, and then this jack and this jack are coupled together through a resistor. And what it's doing is this signal's coming out of your signal generator. It goes into the receiver. It passes through all the filters and the IF and everything of your receiver, and then you pick it up on the probe that's connected to this port. At which point it loops through there and goes into here and combines with this little signal called the marker. And what it's going to make is it's going to make a little inverted bell, like shape of a bell kind of thing, and this little blip is going to be riding on that. And this blip is marking right where you should be adjusting your FM discriminator. Okay, now that's a lot of stuff. If you're not into tuner alignment and things, a lot of that I just said won't make sense. But basically, for those of you who do understand that, to recap what this machine is, it's an RF signal generator with and without modulation. It is an IF signal generator, very accurate one. It's a sweep generator, a marker generator, and a multiplex generator. So it'll even generate the signal that you would use. So here's your 67 kilohertz. Okay. And your multiplex signal, which you can turn on here. You see it? Sorry. Okay. So when we're set to multiplex, what you see right now is pretty much a dead carrier. It is because you do not have a stereo signal. But when I turn on one of the channels, what it's doing is right now it's modulating half of your signal to give you your FM stereo signal. Same thing with this one. If you turn this one on, you could see they combine together, and now you have a stereo modulated signal, and you could see the carrier, the carrier wave here with the modulation riding on it. And I can turn off this side and it goes back to that again. Okay, you have your pilot you can add, and again, this scope isn't going to pick up all this stuff, but This actually can do an alignment of a stereo receiver also. So not just an FM tuner, but an FM stereo tuner it can do. All right. So you can see how versatile this one piece of test equipment is. It is highly, highly versatile. It can do a whole bunch of things, and that's why it's such a valuable piece of test equipment. So again, I have two of these now. This one that I just bought, and then the one that's that's up there. You can kind of see it. See it over there? I got a really good price on this because I think somebody messed it up and didn't know how to fix it. So I got it really reasonably, and I can definitely use a backup because these are pretty delicate machines, and I really like it. There's really nothing else like it out there on the market. I mean, they do have some high-end stereo analyzers and so forth out there, Rode & Schwartz and a couple other companies, and they're many, many thousands of dollars, whereas these can be bought online for hundreds of dollars, which is a lot cheaper. So anybody who does any kind of serious work on receivers, especially like the stuff from the 70s, the classic stuff, this is just built specifically to do that. It's really good for that. So once again, I wasted a lot of your time here talking and talking and talking. I hope you learned a little bit about these and a little bit about how you can test frequency on your signal generators when you're going to calibrate them, the 3 different methods. And hopefully this was a helpful video for you. Maybe it caused you to have more questions than you had before instead of than answers, but maybe that's good too. Ask questions. That's what the comment sections are for, and we can all learn together. So if you like this, give us a thumbs up, and hope you enjoyed the video, and more to come.